All right, so here's a kind of a recap of the central limit theorem. It says if samples of size n, where n is greater than or equal to 30, are drawn from any population with a mean mu and a standard deviation of sigma, then the sampling distribution of the sample means is approximately normal distribution. The greater the sample size, the better the approximation. It's just again saying, restating what we just did above earlier. And this 30 number is just something that some people use in their central limit theorem. It just means the larger it is, but by the time you hit a sample size of 30, we can pretty much assume that the distribution of the sample means is going to be fairly normal. Also, if the population itself is normally distributed, the sample distribution of the sample mean is normally distributed for any size n. So let me back that up. What we're saying is that the distribution of the sample means is going to be normal regardless of the size of n if the population to start with is normal. So back it up to what we just did previously. When we did the shoe sizes, that was not normal, it was uniform. And if we had a large population that we didn't know anything about, then we'd have to make sure, just to be safe, that our sample size should be 30 or more. If we know for sure, like something like we want to look at the weights of people or the heights of people, we know those are normally distributed already, then they say that we can use a sample size of anything. We can use a sample size of 2, and the distribution of the sample means is guaranteed to be normal also because the population was already normal. So that's a thing that we'll come back to when we look at these next couple of problems. If n is equal to, the sample size is equal to 30, it doesn't matter, guaranteed to be normally distributed. If the sample size is less than 30, it could only be guaranteed if we start with some population that's normal. And then for all distributions, the mean of the sample means is equal to the population mean, and the standard deviation of the sample means is equal to the standard deviation of the population divided by square root of n. So now let's see if we can use the central limit theorem to help us with a couple of these basic problems to get the hang of it. So it says the following shows a population distribution for a number of hours of sleep elementary children were getting at one school. Assume the sample size of 81 is drawn from the population. Decide which of the graphs would most closely resemble the sampling distribution for the sample means for your graph. Explain your reasoning. All right, so basically we're saying that most kids get like 8 hours of sleep, but some actually require up to 12 hours of sleep, with an average of these students getting 9 hours of sleep with a standard deviation of 4. Now, the population is not normally distributed, but it's okay because our sample size was 81. Let me see if I can underline that really quick. The sample size was 81, which is basically n is greater than or equal to 30, which means the distribution of the sample means should be normally distributed, such that mu should be equal to mu sub x bar, which is basically the mean of the sample means. And they told us right here that mu is 9. So since we know mu is 9, we know mu sub x is 9, x bar is 9. And then sigma sub x bar is equal to, and really I probably should have written that the other way, just now that I think about it. We really were trying to find mu sub x bar, which is the mean of the sample means, is equal to mu, which is equal to 9. And now I'm trying to find standard deviation of the sample means, which would be equal to the standard deviation of the population over the square root of n. So the standard deviation of the population is right here, it's 4, over the square root of n. N is 81, it said right there, the sample size is 81. So that would be 4 over square root of 81 we can do is 9, and that is basically 0.4 repeating if you put that in the calculator. So all we really have to do is find the one that fits our criteria. This one doesn't quite work. It's not 4. This one doesn't work either. It's not 0.4. We said it's 0.4 repeating, which is this one. So it's going to be choice A. So if we did the distribution of the sample means, it should look like this normal curve right here. All right, let's do this in an actual problem now. It says, use the central limit theorem if possible. For a sample of n equals 36, so that's a good sign. We're above that limit, that threshold of 30, so it doesn't matter what the population looks like. As long as we're above 30, it's guaranteed that the distribution of the sample means will be normal. Find the probability of the sample mean being less than 15 if mu is equal to 16 and sigma is equal to 3. All right, again, they give us the population parameters, which in real life you really can't find these, but this is just to kind of get us used to using the central limit theorem. So from this, to fill out this normal curve, this is supposed to be the distribution of the sample means, not the population. We'll need to calculate mu sub x bar, which we already know is equal to mu, which in this case they gave us is 16. We'll also need to calculate sigma sub x bar, which is the standard deviation of the sample means, which is equal to sigma over the square root of n. And sigma they provided to us was 3. And n they also provided to us was 36 right there. Do you see the 36? So that's equal over the square root of 36. So that will be 3 over 6, which is 0.5. So that tells me that the distribution of the sample means 16 would still be in the middle, and we'd move up or down by 0.5. So we'd move to the left by 0.5, which would be 15.5. Again, by 0.5 would be 15. To the right, that would be 16.5 if I add 0.5. And if I add 0.5 again, that would be 17. It wants to know, what is the probability of the sample mean being less than 15? So that's something we can see using just the empirical rule. 15 is right here, and the chance of the sample being less than 15 would simply be what's right there, 2.3%. So we were able to use the central limit theorem to make a prediction about what the chance of getting a sample that actually has a mean of less than 15. So if this is correct, if all this data is correct, the chance of you actually grabbing a sample of size 36 and getting a mean that is less than 15 is only 2.3% chance. We'll practice some more of these, but this is just like the intro to kind of getting used to what the central limit theorem helps us with, and then from there we'll actually use it to make bigger predictions. I hope this is helpful. I'll start the next video in just a moment.